Hello everyone, this is Chemistry Notes Part 2, the Bohr Model with Ms. Botry. What we're going to start with today is hydrogen. Hydrogen is the simplest element, so that's what we're going to draw out first. So I always start these projects by drawing out what I see on my periodic table so that I can have something to reference back to. So when I look at hydrogen on the periodic table, it has the symbol H. Let's zoom in this spot. And it has this number up in the top left-hand corner of 1, and the number down below is also 1. So if I look over here, I see that top left-hand corner number is the atomic number, and the number down below is the atomic mass, or you'll often hear me refer to it as the atomic weight. Both are used. So we've got 1 and 1. This is the atomic number. You'll see me use a lot of shorthand today. I very rarely write out atomic number, I instead draw the number sign, or you might be more familiar with it as hashtag. This is the atomic mass, or the atomic weight. Okay, so when we're copying this out, we, from this, before we can draw our Bohr model, need to know how many protons, neutrons, and electrons we have. You'll notice the symbols we use here, P and N, are just capitalized letters from the front of their name, but electrons, because capital E is used elsewhere in science, is a lowercase e with this kind of superscript, this little minus sign up above it. So, how many protons do we have? Well, we know from last day that the number of protons we have are equal to the atomic number. That means we have 1 proton. Electrons are also equal to the atomic number. Not always, but in this case, because we are working in atoms. Okay. Neutrons, meanwhile, are a little bit more complex than that. We learned last day how the atomic mass is made up purely out of protons and neutrons. Electrons are so tiny that their mass is irrelevant. So each of the mass is made up entirely out of the number of protons and neutrons we have. We learned also how protons and neutrons each weigh 1. So if I have 3 neutrons, they have a mass of 3 atomic mass units. It's the same thing. So what that means is I can take my atomic mass, I can subtract the atomic number, which is the same as subtracting the number of protons. And by subtracting the number of protons, I'm left with the number of neutrons. So that's what we do. We take the atomic mass, we subtract the atomic number, and we are left with 1 minus 1 gives us 0 neutrons. Excellent. So down here, I'm going to move myself a little bit more central so I have space to draw, because you're going to see how your Bohr models can get quite big. So I'm going to place my P and my N central because protons and neutrons are central to your atom. We're going to place this in a clean circle. This circle we refer to as the nucleus of an atom. And in that nucleus, we find our protons and neutrons. In this case, 1 proton and 0 neutrons. I apologize, I know we talked about nucleus and nuclei when we were in cell biology. Unfortunately, it's the same word. I know it's very confusing. The only thing that a nucleus of an atom and the nucleus of a cell have in common is they're both found central to that cell. They're at the very center. Okay. But we still have to represent our electron. We've got our protons, we've got our 0 neutrons. Where do our electrons go? Well, electrons are whizzing around the outside of that cell, of that atom. Okay, and they whiz around on something we call an electron shell. Okay, and they're whizzing around, creating the shape of that thing. So when you push down on a table in front of you, the thing that you are pushing against is actually that electron whizzing around, creating that shape. You'll never be able to push hard enough to that center to actually press the protons and neutrons. They're kept safe inside. So, like I said, this electron is constantly moving around this electron shell, but I need to be able to see your electron quite easily when I'm going through and scanning your work. So for this year, we always place that electron, that first one, goes up at the very top. Okay? In that kind of north position. And this is our electron. Make sure you fill it in so it's easily visible. Okay, let's look at something a little bit more complex now. We're going to take a look at lithium. So lithium has an atomic mass and atomic number. I'm going to look at our periodic table to find them. I'm going to zoom in a smidge. Excellent. So we can see it has an atomic number of 3, an atomic mass of 6.9. Now, we are always going to be rounding this year. So we're never going to use these fractional neutrons or atomic mass. We have to round. So 6.9, 0.9 falls in that category of 0.5 and above. 0.5 and above, we round up. 0.4 and below, we round down. So for instance, lithium 6.9, we round up to 7. Magnesium over here you see is 24.3. That's 0.4 below, so you would round it to 24. Okay, so we're going to write this down on our page. We've got 3 and 7. Let's zoom out. There we go. So that means for protons, neutrons, and electrons, we have, let's make sure that looks like an N. We have 3 protons, because that's the same as our atomic number. We've got 3 electrons, same as our atomic number. And for neutrons, we take that 7, we subtract 3, and we are left with 4. So let's model it. We have our protons and neutrons. They're in the central of our nucleus. 3 protons, 4 neutrons, not N neutrons. There we go. And remember, that circle is kept clean. Okay. Then in that first shell, there's a secret I haven't told you yet. There's a maximum number of electrons that can be held in each shell. And that first shell has a maximum of 2. Now, there's a very specific place I want you to place them. You may have been told other places. There's a couple different correct orientations, but I only want you to use this one so it's very easy for me to see if you've done it correct and quickly for everybody. So, you're going to place your first one up there, just as we did before, and the second one, I want you to pair it. I know last year you may have been taught to place it down here. I will not accept that this year. You will lose part marks. For the sake of my sanity, they both go paired up at the top. Okay? And then for our next electron, because that first electron shell is filled, we're going to have to place another electron. And again, we place it up there in that north position. Excellent. So let's talk about those magical maximums. What are they? So, as I said, each shell has a maximum number of electrons. The first shell has a maximum of 2 electrons. The second shell has a maximum of 8 electrons. The third shell also has a maximum of 8 electrons. And the fourth shell has a maximum of 18 electrons. Okay, so these numbers might seem a little confusing, but there is actually a trick to help you remember them. It is built into the way that we have organized our periodic table. So I have to zoom up a little more. So if we take a look at our periodic table, we can see that that first row, note, rows go horizontal, not a column. So in that first row, we see all we have is hydrogen, and our periodic table is a little funky. Hydrogen gets repeated because it acts both as a metal and a nonmetal, but there's just hydrogen and helium. Those are the only two elements, and so the maximum in the first shell is 2. In the second row, we have 1, 2, 3, 4, 5, 6, 7, 8 elements, and our maximum is 8 electrons. Okay? Same goes for our third, also 8. Our fourth shell has 18 elements all the way across, and 18. We're not going to go into the fifth and sixth. At that point, we start to use another model, and you'll see that next year. Okay, so it is built here into your periodic table. If you forget, there's 2, and then 8, and then 8, and then 18. And if you're feeling like you don't have enough time to count out all of the ones in that fourth row, you can actually use your column numbers across the top. But you can only use that in the fourth row because they count all of your transition metals here in the middle, and we don't see them in the third or the second and third shells. Okay, so I've also been talking to you. There's very specific placements that I want. So let's talk about what those placements are. So when we're taking a peek at those very specific placements, what I'm expecting is we always start at the central, and we're going to draw a 4 shell, so it's going to be big. If you're drawing this for yourself, you want to make sure you're placing it kind of central to your page. We always start with our protons and neutrons in our nucleus at the center. Clean circle, no electrons, or I will dock marks. First shell, okay, is going to have 1 and 2. Your first and your second electron placed there up at the top. I'm just placing mine a little bit off the circle just so you can see the numbers a little bit better for today. Okay. Then we have our second shell. So this is the first shell where things start to get a little bit more complex. You saw how 3 always gets placed up there at the top. Oh, you can see I'm already starting to take on an angle. You want to try and keep it in the 4 cardinal directions, but if things angle a little bit, that's okay. Okay, so first electron in that second shell up at the top. Then we go to fill each of the other 4 cardinal directions. So we've done north, now we do east, south, west. Okay, but what we have to do is we have to fill each and have those 8 electrons because we've only got 4 in that second shell. We got to fill it to its max. So now we go 7 here, 8. And some of you might be thinking, wait a second, but 8 was the maximum. Yes, but we started counting in the first shell. So we only have 6 in our second shell right now. We've got to have 8 just in the second. So 8 goes there, then 9, then 10. Okay, now we've got 2 full shells. We need to now draw our third shell. It's going to look just like our second shell. So 10 was our last one, so 11 goes up here, 12, 13, 14, 15, 16, 17, 18. Excellent. Now, fourth shell is where things start to get a little funky because now we're not just working in this world of 8 electrons in that maximum. We've got to fit 18 in. So things start to get a little bit funky. So 18, next one is 19. We fill out that first 20 like normal. 24, 25, 26. Okay. And then we start to half our distances. Because electrons are pushing away from each other. It's like two negative ends of a magnet. If you bring a south end and a south end, they push away, they repel. So 26 is here. 27 goes here and starts to half your distance. So 27, 28, 29, 30. Okay. Then we do exactly what we were doing before. We pair them. 31 goes here, 32, 33, 34. Okay. But at this point, in our outermost shell, we've had 8, and then we've had 8 again, so we've had 16 in this outermost shell. We got to get to 18. So where do we place those last 2 electrons? So there are a couple different places. This year, the places that I want you to place them is that your 17th electron is going to go right here in that first half distance. So this is going to be your 35. Okay. And I want your 36 to go there. Okay. So you do your 4 cardinal directions, then you tilt it on its axis and you do your northeast, your southeast, your southwest, your northwest, and then your 2 leftover odd men out, 35 up here, that first quadrant, 36. Oh, sorry, I placed 36 wrong. That's my mistake. This should not be here. It should be between east and southeast. My apologies. That's quite confusing. 36 goes right there. Okay? Excellent. So, we are going to draw our first one. With this new knowledge, we're going to draw a monster. We're going to draw arsenic. So, when we look at arsenic, we're going to take a look at our periodic table. Okay. We find arsenic down here. Let me zoom in a bit for you. Has an atomic number of 33. Atomic mass of 74.9. 74.9, we round up to 75. So 33 and 75. 33, 75. We got our protons, neutrons, and electrons. For our protons, we're going to have 33, of course. Our electrons, also 33. And for our neutrons, 75 minus 33 gives us 42. Okay, so I'm going to show you the tricky way to do this first. It involves a little bit more math. The second way to do it is going to be much more shorthanded. So, the tricky way to do it first. We got to figure out how many shells we have in this crazy guy. So, you're going to look at it and say, well, 33, subtract the maximum of the second shell. I know that I still have 31 left over. So that tells me that the first shell is full. Okay, I now have 31 left. Do I have an 8 in there? Well, yes, I do. That leaves me with 23. So that tells me my second shell is also full. Okay? Well, take that 23. Do I have room for another 8 to pull? I do. So that leaves me with 15. That tells me my third shell is full. 15 does not have 18 in it. So that tells me there are going to be 15 electrons in my fourth shell. Okay. So, this is one way to do it. You can also, the worst way you can do this, there's a third way that I'm not encouraging anyone to do, but you might be tempted to do, is to count every single electron out. I'm warning you now, if you choose to do that, chances of you misplacing an extra electron are very high. So, math solution, or I promise you there will be a shorthand version to do this. So, I'm going to flip the page, and we're going to draw this monster of a Bohr model. Here we go. So, I want to move it central because I know I have 4 shells. I am not going to have tons of space if I start out too far. So let's go here. So, protons are going to be 33. Neutrons are 42. Place that in my nucleus. I remember no electrons in the nucleus. First shell I learned last day. Goes 2 up at the top. Second shell, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Third shell, 1, 2, 3, 4, 5, 6, 7, 8. And fourth shell, I know that I only get 15.